So you just watched a video showing the creation of some various standing wave patterns. Let's take a look at why these happen. So in this animation, we'll be able to see two different waves present in the same medium at the same time. One of these waves may be a wave, an incoming wave, a wiggle that's moving, say, to the right, and another wave headed the opposite direction, which comes from reflection. So standing waves only happen in situations where we have the reflection of waves, and we have one wave headed in one direction, one headed in the other. They're going to overlap, and they're going to interfere with each other. So here we see the two wave patterns interfering with each other, and the animation at the bottom shows what their sum is equal to. So as time goes by, this pattern evolves. We kind of move this to a few different moments. So like at this particular instance, we get complete destructive interference, where the bottom wave completely cancels the top wave. Crest and troughs meet, trough and crest meet. And then a moment later, they shift over so that they're going to add up constructively, and we get an extra big crest and an extra deep trough. So we kind of alternate between constructive and destructive interference. But there are particular points called nodes that never move, that are always destructive, and antinodes, which we have maximum oscillation. So here we can see an antinode oscillating up and down, and a node where there's no movement at all. So this is the standing wave. There are a whole bunch of patterns like this that can exist in strings that are fixed at both ends. If a string is fixed at both ends, there must be a node at either end. The simplest pattern is just one lump moving up and down, and then the next pattern is 2, and then 3, and then 4. There's an infinite number of these. So a lot of times they're drawn like this, where we can see it's not actually in both positions at the same time, but it's flipping back and forth between the top and the bottom position. This is the most important. The simplest pattern matters the most. It's the fundamental, and it matters the most because this is the main note you hear when something vibrates back and forth. So we call this the first harmonic, and then we have the second and the third and the fourth. You'll notice that the harmonic corresponds to how many lumps we have moving up and down. So if I showed you a picture that had 24 lumps, then you would know it was the 24th harmonic. Now, when a string is vibrating in an actual musical instrument, it's a bit more complicated than just having a single one of those harmonics playing. So for instance, when you pluck a guitar string or you strum a guitar string, you're not strumming it exactly in the center. Perhaps this is of course exaggerated, but maybe you pluck it down here near one end of the guitar. And this particular position of the string could be a representation of 3 different harmonics at the same time. So for instance, here the red would be my fundamental or my first harmonic, the blue would be my second, and the brown would be my third. If all 3 of these are present at the same time, then they're going to add up. And so we can see at the left end of this pattern that they all have sort of a positive height to them. So the 3 heights all add together to produce a large height. And down here at the right end of the pattern, we've got the red and the brown with positive, and then the blue is a trough, it's a negative. So there's some canceling happening down here, so we have an asymmetric pattern. And what's really fascinating is that as the string vibrates, this is what its motion looks like, its shape looks like, but your ear is actually going to hear all 3 of these patterns at the same time. And they sound nice together. It's one reason why plucked and strummed strings are so good for musical instruments, is because these harmonics, there's a nice mathematical pattern to these different oscillations that we'll derive in just a moment. So all kinds of examples of this in musical instruments, whether it's an instrument, a string you pluck, like the bass fiddle in this case, or draw a bow across it to cause the string to vibrate, or in the case here's a piano, and the inside of the piano is being struck by hammers. And standing waves exist in all of these instruments. And understanding these standing waves allow us to know what notes are being played. So let's take a look at that next, and we'll derive an equation to figure out what frequencies we hear.